Consider an observable AX. Examples could be velocity in a state space, where this is point in state space. Another example could be energy dissipation rate. With this, if you imagine you have a turbulent pipe flow or some such thing, this is a position in state space, which means instantaneous dispositions of velocities of the fluid. And these things are rates per unit time. Let's call it accumulated observable. Defined as an integral from time t to time 0 t of the observable observed on the trajectory. Examples would be, if this is velocity, then this will be the position, time t. And if this was dissipation rate of the energy instantaneous, then this would be total energy loss. Let's say, due to the friction of a fluid, having started in some state of the fluid and gone time t, and using this formula. Now you can define a time average on an orbit. Now remember, orbit is all states you can reach moving forward in time from initial state. So that by definition is a time invariant quantity. So it's an invariant property of the orbit. So A, average, but it depends on particular orbit. X0 is the limit. T goes to infinity. The integrated observable divided by time, or accumulated observable. It's particularly nice on compact orbits. So if you, for example, if you have a periodic orbit, then we can define A evaluated on P. So the property we aim to evaluate on the orbit. And that's very nice because we can write it as AP over TP, just one run around the orbit, where AP is defined as integral from 0 to 1 period, 1 return on the orbit, where X is any point on the orbit. So orbit is a set of points, so it's a subset of state space associated with the orbit, one-dimensional. So space average. Consider E beta to the and remember, A is something that depends on the state that you're evaluating it, but it also depends how much time has elapsed when you started being in the state. So this guy is doing some time integration on it. So this thing depends on the time. And this beta is just a convenient parameter to manipulate this kind of object. For T large, so this is an average of things that increase exponentially with time, because every A is increasing exponentially in time, because roughly being accumulated proportional to the time along the given trajectory. This is probing all orbits. That's why we're averaging over space. So this is not just one orbit. And whenever you have a bunch of exponentials, all of them increasing with one parameter like time, you expect that sum to be also behaving exponentially. So leave it to you to convince yourself that that's how it works. And that says that this sum, as the time grows, is going to look like E time number here, which depends on beta, and it's averaging basically of different trajectories in a way that's controlled by this beta. In other words, the object of interest for large time is this exponent here, and that's defined as a limit. T goes to infinity, 1 over t, and then logarithm. This is a positive quantity because it's sum of positive numbers. remember each accumulated observable is going roughly, it's going linearly. It's our assumption this time. So this is a sum of things that individually all grow like e to the beta t time average value of this observable. So if you take a logarithm of that quantity, that's going to pick up the dominant behavior proportional to t, and this will take care of it, and this is expected to have a limit.